This thing of beauty is called an orrery. It's a mechanical representation of the workings of the solar system. It's an exquisite piece of engineering and represents an idea that dates back to the 17th century, that the universe runs like clockwork.
300 years later, and our ideas about how the universe works have moved on. But the idea of the clockwork universe is still seductive and relevant today. This planetarium is the modern equivalent of an orrery, except here we can show not just the orbits of the planets, but also the motions of the stars and even the galaxies.
So in tonight's programme, we're going to be playing with a clockwork universe, travelling backwards and forwards to the distant past and to the far future.
And we'll be finding out what happens when that clockwork goes haywire, scattering stars, planets and galaxies. Welcome to the Sky at Night.
The Royal Observatory Greenwich is the perfect place to come to talk about the clockwork universe, because it was here that the idea began to take shape. The observatory has played a key role in our understanding of the universe. When it was first built in 1675, it was with the specific purpose of accurately measuring the position of the stars and the planets for the purposes of navigation, so the sailors of the British Navy could find their way. But it is also now home to the Peter Harrison Planetarium, where we can find the ultimate modern orrery.
The planetarium software contains a remarkably detailed 3D model of the universe. And yes, you can plot the positions of the 8 planets of the solar system, but it also includes data from some of the most advanced telescopes around. It includes the locations of tens of thousands of stars and galaxies. Critically, it's not just a snapshot of the universe. The software knows about how the stars and the planets move, and so we can use it like a time machine. By scrolling backwards and forwards through the ages, we can see how the night sky would appear. And that's exactly what we're going to do in this programme. We'll be discovering how studying the clockwork of the galaxy is giving us dramatic new insight into our sun's history.
It didn't come from here. It actually bounced off a spiral arm from 2,000 light years away and popped out.
This is staggering. I mean, I genuinely didn't know this.
On an even more epic scale, we'll be discovering what will happen to our galaxy billions of years in the future.
And in the spirit of playing with the clockwork universe, we've asked mathematician Hannah Fry to investigate the claims of the ancient study of the movement of the planets, astrology as it's known.
Look at that for a balance of the chart. All of the planets are underneath the horizon. None of them are above.
But we start with the story of how the clockwork mechanism of our solar system was spectacularly reset early in its history.
The solar system was formed nearly 5 billion years ago. But we think that the early solar system was unlike the one that we see today. And the layout of the planets was very, very different. We think that the rocky planets, Mercury, Venus, Earth and Mars, formed pretty much where we see them today. But it's with the giant planets that things start to change. We think that they formed in places very different from the ones we see them in now. Take Neptune, for example. Today it orbits at a distance of 4.5 billion kilometres from the Sun. But we think it formed at less than half that, just 1.8 billion kilometres out. In fact, Neptune was so much closer that its orbit was inside that of Uranus, a reverse of today's position. And both planets were so close to the Sun that they would have been visible to the naked eye from Earth. So how did we get from this initial alignment of planets to the solar system we know and love today? Maggie's been talking to Richard Alexander to find out.
One of the best ways we have to explore the evolution of the solar system is to build computer models that replicate its early days.
The most popular model and the closest thing we have to a standard model for the history of the solar system is the so-called Nice model, which is named after the French city where it was initially developed. And the premise of this model is essentially that the 4 giant planets were in a much more compact configuration in the early solar system than they are today.
So can we see the model?
So if we run the model, the orbits of the 4 giant planets are shown here as the circles.
So terrestrial planets aren't shown here, but they'd be
No,
right.
terrestrial planets are too small to fit on this plot. And then each of the green dots represents one object in the
So
Kuiper
a chunky Kuiper belt object.
And so what happens is you see this gradual, slow evolution where Neptune and Uranus are moving gradually outwards.
Okay. What would cause this migration?
It's the interactions between the giant planets and the Kuiper belt objects. So these are the dwarf planets, the asteroids, the comets that we see in the outer solar system. And what happens generally with the ice giants, Neptune and Uranus, is that the small bodies get a gravitational kick.
Each time they go past.
Each time they go past. It's a close encounter that kicks the individual Kuiper belt objects inwards. And because momentum is conserved, the small objects can get scattered inwards and the giant planet moves very fractionally outwards.
In this first stage of solar system evolution, the giant planet's migration was too slow to get them to where they are today. Something else was needed, and it came 3.9 billion years ago, when Jupiter and Saturn entered what is known as a resonant pattern, where Jupiter orbited the Sun exactly twice as often as Saturn. It meant that they passed each other at exactly the same place in each orbit. That interaction massively amplified the gravitational influence of Jupiter and Saturn, causing the whole of the solar system to suddenly go haywire. But it looks fairly stable.
It looks fairly stable, and it is for 800 million years or so. But then this resonant crossing event happens, and so this is where Saturn crosses this special location relative to Jupiter. It's a very strong gravitational interaction, and the whole system expands very rapidly.
So it goes eccentric.
It goes eccentric, and that causes the outer planets to move outwards very rapidly as well. And you scatter a lot of the Kuiper belt objects. A lot of them get flung out of the system, a lot of them get scattered in towards the inner solar system, collide with the Sun, collide with the inner planets.
It's thought this scattering of Kuiper belt objects is responsible for a dramatic event in the early history of the solar system called the Late Heavy Bombardment. A rain of comets and asteroids that peppered the inner planets for around 100 million years. It left the familiar pattern of craters on the Moon and Mercury, and it would have had an impact on the Earth as well. So there's strong evidence to show that the gas giants really affected the planet we have today here on Earth, and possibly life here on Earth.
Yes, I think so. One of the open questions is how Earth gained its water, because if Earth formed at or close to where it is now, it probably couldn't have held onto a lot of water, because the early solar system would have been too hot to hold onto ice. Ice would have evaporated. And so if we want to move volatiles, as we call them, ices, water, carbon dioxide, from the outer solar system, where we know they exist, to the inner solar system to generate water on Earth, then the most likely way to do that is one way or another through Jupiter and Saturn using their gravity to fling objects inwards.
So yeah, possibly responsible for life here on Earth.
Potentially.
Well, that's been fantastic. Thank you very much.
Thank you very much.
The big idea that underpins our understanding of the movement of the stars and planets is, of course, gravity. The idea that two massive objects exert an influence or pull on each other. And that got us thinking, just to be provocative, what if we were to look at another area that claims that the stars and planets exert an influence? Astrology. We asked mathematician Hannah Fry to look into astrology's claims, and also to investigate the ancient link between astrology and astronomy.
Astrology. On the face of it, it's a bit of a strange one. The idea that the position of the planets or constellations in the sky can have an effect on individual human lives. But for thousands of years, it was cutting-edge science. The Chinese, the Indians, and the Mayans all had systems to predict terrestrial events from celestial observations.
To many of us scientists, it seems remarkable that astrology is still so popular today. But equally, the scientific approach means that rather than dismiss astrology's claims, we should test them dispassionately. The first thing I'm going to do is have my own horoscope read by astrologer Barry Street.
Hello, Barry.
Hi, Hannah.
Lovely to meet you. So, got a copy of my birth certificate and my baby book.
All he has to do is enter my time, date and place of birth into his computer. And in seconds, he has a chart which shows the exact position of all the planets at the precise moment I was born.
Here we have your birth chart is there. Look at that for a balance of the chart. All of the planets are underneath the horizon. None of them are above.
And from the position of those planets, Barry says he can interpret my personality.
Each planet represents an area of life. Your Mercury is in the 5th house, the house of creativity. You're a writer of some sort, and it's in the sign of Aquarius. You're a scientific sort of writer.
Well, that's true, but I do have the feeling that Barry may just be reading me, monitoring my reaction for clues and telling me what I want to hear.
You're tolerant of most things, but not hypocrisy and lies.
I'd say that one's true of almost everyone.
No?
So I've just had my horoscope read, but the thing is, I don't believe in astrology. I don't see any physical mechanism which means the planets could affect my personality. But if I'm being absolutely truthful, I also sort of forget that I don't believe in astrology, because when he was reading my horoscope, there were some things that felt like they were really personal. But I suppose they probably could apply to everybody. What we really need is a much more scientific way to assess whether or not astrology has any merits.
There have been a number of scientific studies that have tried to test astrology. Most famous was the work of a French psychologist, Michel Gauquelin, who in the 1950s published a study that appeared to show a link between sporting ability and the position of Mars at birth. So this is the chart that Gauquelin constructed for sporting champions in his paper that he released in 1955. This is the horizon. This here is the visible sky. This is the hemisphere below the horizon. And this line shows you how many athletes were born when Mars was in a particular position. Now, quite quickly, you can see that there are two very clear spikes here. One just after Mars rises and another after the zenith, after Mars culminates. At the time, this was considered to be a statistically significant connection, one that became known as the Mars effect, and it caused quite a stir. Many people, even some scientists, thought Gauquelin had established a proof for the concepts of astrology, that the positions of the planets at our birth really do have an impact on our lives. But to mathematicians like me, the result is not so groundbreaking. If you toss a coin, there's a 50% chance that it will come up with heads. So if I end up with 10 heads in a row, you'd be well within your rights to be suspicious that something a bit dodgy was going on, that this coin was disproportionately coming up with heads. But now imagine that I had 100 coins, or maybe even 1,000. It becomes increasingly likely that one of these coins will come up with 10 heads in a row. But this time, you can't just pick out that coin and accuse it of being biased. It's just a natural result of randomness. And that's what happened with the Gauquelin study. He was looking for so many different correlations, thousands and thousands of birth dates with 10 planets and 12 positions in the sky, that he was bound to come across some spurious patterns. And that's what the Mars effect is. He didn't adjust for the number of combinations, and the result is just there by chance. No scientific study has ever found reliable evidence to back up the claims of astrology. But that's not to say that it doesn't have some scientific background. In fact, until just 300 years ago, astrology and astronomy were virtually indistinguishable. Galileo, Copernicus, and Kepler were all keen astrologers. To find out more, I've come to see astronomer and writer Stuart Clark.
So, Stuart,
what seduced these great names into astrology then?
It was thought that the heavens were God's realm, and so nothing would happen up there without a reason. Kepler became interested in why astrology worked. He said, what is the nature of the mechanism that brings the influence from the planets and resonates inside us? He knew that the tides follow a particular 19-year cycle. He also knew, of course, that the moon's orbit around the Earth follows a 19-year cycle and that the two are synonymous with one another. So he knew that the moon was producing the tides by some invisible, unseen influence. And he reasoned to himself that if the moon can affect the mighty ocean, then it must surely, he said, have an effect on the fragile human soul.
Which sounds quite sensible in a way, really, having something that happens, a position of an object in the sky having an influence on Earth. It sounds like a logical conclusion to draw.
Absolutely. A firm hypothesis based on observation. It fell down later in the century because Newton derived his law of universal gravitation, and there we saw exactly what the influence truly was and the nature of it. At that point, astrology really began to die away. There was just nothing that could be measured, nothing that could be tested.
So does astronomy have a lot to thank astrology for?
It really, really does, because the key question in astrophysics today is, how does a celestial object work? How does it influence the things around it? And those were the kinds of questions that Kepler was asking in his personal investigation of astrology. How does it work?
It's easy to think of astrology as a pseudoscience. And in its modern guise, I think it is. It's fun to have your horoscope read, but I couldn't find any evidence to suggest that it actually means something. But it's also important to remember the subject's rich history, how it's the embodiment of an age-old desire to understand the motion of the planets in our sky, much as astronomers do today.
To see how prevalent the ideas behind astrology were, you need to see this. It's a horoscope drawn up by the first Astronomer Royal, John Flamsteed, to mark the occasion of the laying of the first foundation stone for the observatory in August 1675. It was seen as an auspicious day, but I'm not too sure how seriously John was taking it, because written here in Latin is, "I hope my friends refrain from laughing." After the planets, the next stage in understanding the clockwork of the universe was to study the movement of the stars. This book is an astrographic catalogue taken here in Greenwich in the year 1900. If we look inside, it has lots and lots of information. It has the plate number, the date the plate was taken, and then row after row of what's meant to be the permanent position of thousands of stars. This is volume 1 and volume 2's there. This must be an epic piece of work. But the truth is, this isn't a permanent record of the stars at all, because given time, each one of these stars will move. The stars don't move quickly, but some travel fast enough that if you photograph them over months or years, you can see them moving. This is Proxima Centauri, the closest star to the Sun. Photographed over 10 years, you can clearly see it moving relative to the other stars. And given enough time, it will become apparent that all the stars are moving. It's called proper motion, and it means that over time, the pattern of stars, the map of the night sky that we see from here on Earth, will change.
The model of our galaxy in the planetarium's computers includes the proper motion of thousands of stars, and we can use it to see how the night sky changes over time. I'm sure that since humans evolved, they've been looking up at the night sky. But not the night sky that we see. This is what the sky would have looked like when the first humans emerged in Africa 200,000 years ago. And it's an uncanny sight. Some of the familiar constellations are there, but others are distorted beyond all recognition. And if we go back further, let's say to 1 million years before the present, then things change completely. The familiar constellations are gone, revealed to be nothing more than temporary, chance alignments of random stars. The constellations we see today would have been unfamiliar to our ancestors and completely alien to our descendants. This is Cassiopeia, one of the most recognisable constellations in the sky, but it will change dramatically over the course of the next million years, becoming completely unrecognisable as the stars travel on their own paths, going their separate ways. Tracking the motion of the stars can reveal the journey that they make over their lifetimes. It can even help unravel our own sun's history. And as I found out from Professor Jerry Gilmore, our star has been on quite an adventure.
A star is formed probably in a cluster, but certainly in a star-forming region, something like Orion, it's full of young stars. And these stars diffuse away slightly just because the Milky Way is rotating. But then as stars move out through the rest of the Milky Way, they're scattered around a bit, not by actually hitting other stars, but by coming close to another star. They get a tiny tweak in their orbit, and these tiny tweaks build up over time. So eventually, after a long time, all the stars have forgotten their initial conditions, and they're moving around in their own peculiar little way.
So hang on, so stars can move, because I think of stars rotating in this disk, they're supposed to go sedately around the galactic centre, and you're saying stars can move in and out as well?
That's right, yes. And when stars move into a spiral arm, they can bounce, they hit a resonant bounce off the gravitational field of the spiral arm, and they can jump huge distances, thousands of light years.
And this process must have happened to the sun as well.
Oh yes, well certainly. See, the funny thing about the sun is that it probably didn't get formed anywhere near where it is now. It probably was formed quite a long way into the Milky Way, because the sun has got too many chemical heavy elements compared to most stars near it. So it's a little bit odd. And the simplest explanation for that is that, well, it didn't come from here. It migrated here. And so it actually bounced off a spiral arm from 2,000 light years away and popped out.
This is staggering. I mean, I genuinely didn't know this. That's staggering. That means that the conditions where the sun formed would have been very different.
They could have
from
been.
where
Yep, they could have been, yeah.
While we can plot the motions of stars over a few millions of years, these incredibly complex gravitational interactions in the galactic disk makes plotting their movements over longer periods much more difficult. That means we may never be able to work out where our sun was born, but we might be able to discover something about our origins by finding the sun's siblings, the stars that were born in the same cluster. So any hope of finding the companions for our sun?
To answer a question like that, you've got to say, well, not only where is the sun now and how's it moving, but what's it made of? Because the only fossil evidence of the conditions at the time of its birth are the chemical elements in the star's atmosphere. So we have to measure those as well.
So it's the mix of stuff that makes up the star?
Yes, that's right. Every little region is slightly different from another pattern. If we can see those tiny differences, then we'll be able to say, aha, you went to the same school, you were the same place, you're wearing the same tie. There's an old open cluster called M67, and that's got a couple of stars in it that are very suspiciously similar to the sun, and so maybe we were once friends.
While many of the changes in the night sky take place over long periods of time, there are other shorter-term changes, and it's these that Peter's looking at this month.
When you go out and look up at the night sky, the stars appear to be essentially fixed in position. But there are short-term visitors that can appear to move among them quite rapidly, and the most spectacular of these are comets. For thousands of years, people have been mystified by the sudden appearance of comets in the sky. But we now know that their movements are also driven by the gravitational clockwork of the solar system. Last November, comet 67P Churyumov-Gerasimenko caught the world's attention when the probe Rosetta went into orbit around the comet and landed the Philae lander on its surface. Since then, Rosetta has been sending back incredible close-up images of the comet. These latest images, released just a few weeks ago, show the comet emitting great jets of gas and dust as it passes close to the Sun. And now we have a chance to observe it from the Earth as well. It's not going to be a spectacular comet. It's still pretty faint and it's quite small. But if you've got a telescope which is 8 inches or larger, then you should be able to see it visually through that. Or if you've got a camera with a regular lens fitted to it, then a long exposure should be able to pick it up, but it will be quite tiny in the frame. Now, to see it during the middle of September, you need to look towards the east from about 4 o'clock in the morning. Now, if it's clear, and it's not looking that great for us at the moment, you need to find somewhere which has got a nice low horizon towards the east, and a beach like here is perfect for that. You can find full details of where to find the comet in my star guide on the Sky at Night website. Back on our beach, the clouds cleared and we finally got a view of the comet just as the skies were brightening before dawn. Okay, I'm going to have to put it up on a computer screen to actually look at it closely enough to work out what I'm seeing, but there is an object which I'm looking at here which has got the characteristics of a very small fuzzy comet. That might be it, which would be amazing as we've got it just before dawn. The sky is getting very bright, but I think we've been remarkably lucky to have actually got a clear slot in what was a very, very cloudy sky when we arrived, and that's just fantastic. And here it is, a picture of a very small, faint comet. It's amazing to think that there is a tiny spacecraft buzzing around it. Later in the month, on the 28th, there's one of the most dramatic and shortest term events visible in the night sky, and that's a total eclipse of the moon. Now, this is a fairly rare event which occurs when the moon is full and the Earth sits directly between the moon and the sun. The disk of the full moon will be slowly consumed by the Earth's shadow, turning it a spectacular blood red. It occurs in the early hours of the 28th, starting at 0207 BST for the main eclipse. Now, you need to locate the moon, which is in the south-southwest at that time, but to be honest, the full moon should be pretty easy to find. It takes about an hour for the moon's disk to slip into the Earth's shadow, and totality lasts for about another hour again. Now, this is really one of the main events of the year, so something to really look out for. So let's keep our fingers crossed that the weather stays clear.
The movement of the planets and stars is relatively obvious from Earth. But the Clockwork universe operates on another level, which is much harder to detect: the movement of galaxies. Yet even with galaxies, the relentless predictability of gravity means that we can still run the clock forwards or backwards. Each of the dots in this graphic representation are individual galaxies, as mapped by the Sloan Digital Sky Survey. And we find that they are all involved in a gravitational dance with each other. And like people with two left feet, sometimes the dance goes wrong and the galaxies crash into each other. In 4 billion years' time, our galaxy, the Milky Way, will collide with the Andromeda Galaxy, and the skies from Earth will change dramatically. This animation shows what we think will happen when the galaxies collide. Although the collision looks dramatic, there's very little violence in it. The stars that make up the galaxies are very widely spaced, so they're unlikely to run into each other. What will happen is that two galaxies will form a huge elliptical galaxy, changing the skies of Earth forever.
Well, that's it for this month, but when we come back next month, we'll be talking about the solar system's volcanoes.
In the meantime, get outside and get looking up.
Good night.